So up to now, we've looked at several things involving the binomial theorem, including expansions of simpler sets of brackets and then much more complex ones. What we're going to look at here is we're going to look at calculating coefficients, powers, and actual physical general terms associated with expansions of brackets using the binomial theorem in the general format that we know. So there's several things that we have to be able to do. So one of them could be calculating coefficients of terms that have got set powers, so maybe ones that are independent of x, calculating what values we have to set the r to in our expansion of nr if we are given a set power such that we get a coefficient of a certain number. There's a variety of different things that we have to be able to do. We can also look at ratios of terms. What we're going to do in this video, I'm going to walk you through a couple of examples of them, but I'm also going to tell you kind of the general way to approach them and show you how this can work. Because these types of questions, if you can approach them the same way and approach them in the correct manner, you should actually be able to manage them no problem at all. So let's have a look at how we'd approach this type of problem. And we always want to think about it in the same way, in the same manner. So first thing we want to do is we want to find the format of each term in a generic way, i.e. how would the term look written as a single part and a single variable involving x, where we've got a power involving n and r such that we can manipulate it. We want to simplify it as much as possible because you've got to remember we'll be bringing in an x and a y, so the two parts within our binomial expansion, and putting them together. So we want it written in the simplest format. We then want to use the n they give us, so they might give us the highest power, they might not, and we want to use this to find the r, which gives the required power we need, or we can use that to then find the r, which maybe gives us the coefficient that we're going to be looking at. We then have to calculate these coefficients, or the terms, or the information in general that it wants us to do, and then be able to manipulate and use these terms to answer further questions. As I said, maybe looking at the ratio of one term to another. So I'm going to show you a couple of examples of this. First example is, imagine I want to find the term independent of x in this expansion here. Now the first thing we want to do is we want to look at the general term of the expansion. So what's it going to look like? Now we know that for the binomial expansion, the general term is going to be something of the format nr x to the n minus r y to the r. If we've got a bracket that is of the format x plus y to the n. This is how we're going to expand it. So what we do is just focus on this singular part here. How is a single term going to look? Well, if I equate this bracket to what I've got here, I know that my x part of my expansion is going to be the equivalent of the 2x squared, and the y part of my expansion is going to be the equivalent of 1 over 3x. I also know that my n is going to equal 6. So I could take all that information and plug it into here. I know then my general term is going to be given by 6r, that'll be the coefficient, times the x to the n minus r, which is the 2x squared. So I've got 2x squared to the n minus r. I've then got to multiply that by the y to the r, so times that by 1 over 3x, all to the power of r. What I now want to do is expand it and get the like parts together. So for example, this bracket here, 1 over 3x, what I can do is write that as 3x all to the negative 1. If I bring it up so it's written as a power, I can write it like that. And that's the equivalent of then 3 to the negative 1, x to the negative 1. But if I have this whole thing to the power of r, what that is the equivalent of is 3 to the negative 1, x to the negative 1, all to the power of r. So that then gives me 3 to the negative r, x to the negative r for that term. If I then look at expanding the 2x squared to the n minus r, well, one thing I've got to remember is that n is equal to 6. So that is the equivalent of saying 2x squared times to the power of 6 minus r. What I then do is expand each of these on their own. So I get 2 to the power of 6 minus r, and I'm going to have that multiplied by x squared to the 6 minus r, so that's 2 times the 6 minus r. So my x part here is going to be given by x to the 12 minus 2r. So if I put all of that together in one go, what that then means is my binomial coefficient is going to be given by 6r. I've then got 2 to the power of 6 minus r times 3 to the negative r. So if I put the numerical parts together and then group the x's together, and then multiplying that by x to the 12 take away 2r times x to the negative r. What I can then do is, because these have got the same base, both of x, I can multiply these together and combine the indices, i.e. add them together. So what I then know I've got is 6r 2 to the 6 minus r times 3 to the minus r times x to the 12 minus 3r. Now I've got to think what it wants. Well, it wants the term independent of x. So what that means is I want x to the power of 0. So I have to focus on this, and I have to say to myself, right, what value of r gives me x to the power of 0? So to solve that, I say, right, so 12 minus 3r is equal to 0. What is r in this case? Well, in this case, r is equal to 4. So I know that if r is equal to 4, the x term disappears. So what I can do is take the 4 and plug it into all the parts here that are r, and I'll end up getting my final solution. So my binomial coefficient part is given by 6, 4. It's then going to be times 2 to the power of 6 minus 4 times 3 to the power of negative 4. All I now have to do is work through all that, calculate the whole thing, and then I'm laughing. I'm going to get what I want. So if I do that, my 6, 4, that's going to give me 15. My 2 to the power of 6 minus 4, well, 6 minus 4 is 2, so it's 2 squared. So that's going to then be times 4. I can then look at my 3 to the power of negative 4. Well, that's the equivalent of 1 over 3 to the 4. 3 to the power of 4 is 81. So I've then got 15 times 4 over 81. If I do that and then I simplify as much as I can, what I get is 20 over 27. So that there would be the term independent of x, i.e. that would be the term that I would get there. So it's working through that and using a bit of logic. Another kind of question that I'm going to look at is imagining that if x was equal to a quarter, find the ratio of the 8th term to the 7th term in the expansion of 1 plus 2x to the power of 15. So I need to know what the 8th term is, I need to know what the 7th term is, and then I find the ratio of them, i.e. I do the 8th term divided by the 7th term. So my 8th term, I'm going to call that U8. I know that n is 15, so that's going to be given by 15, and this is where the trick comes in, because 15, 0 counts as the first term. It's not the 0th term, it's the first term. So the actual term number is one less than where I am. So the 8th term is actually given by 15, 7 from my binomial coefficients. It's then going to be times 1 to the power, remember it's n minus r, n is 15, r is 7, 15 minus 7 gives me to the power of 8, then it's going to be times the 2x to the power of r, which is equal to 7. Quick check here, add the two powers, 8 plus 7 is 15, that's exactly what you should get. What I then do is I take this, calculate my binomial coefficient, calculate 2 to the power of 7, and combine them. Once I do that, I end up getting 823,680 x to the power of 7. So a nice, simple, easy term. I then do my 7th term, so I'm going to call that u to the 7. And again, remember the trick, our binomial coefficient is given by 15, 6. That's then going to be times by 1 to the power of 9 times 2x to the power of 6. Again, the check, add the powers, 9 plus 6 is 15. Put that all together, so calculate my 15 sixth binomial coefficients, times it by 2 to the power of 6. What you end up getting is 320,320 x to the power of 6. Great, so I've got my two terms there. What I now need to take into account is the fact that I was told x was equal to a quarter. So if x is equal to a quarter, what I have to do is plug x as a quarter into both of those and calculate it through. Now luckily, something like this with these sorts of numbers in it will be in a calculator paper, so we can put it in as long as we enter the numbers correctly. What I end up getting is my 8th term, u8, is given by 6,435 over 128. My 7th term, u7, is given by 5,005 over 64. I then want the ratio of the 8th term to the 7th term, so what I do is I do u8 divided by u7. So I take this term here, and what I do is I divide it by this term here. Again, stick that in a calculator and work it all through. What you should end up getting is 9 on the top, 14 on the bottom, 9 over 14. So that there is the ratio of my 8th term to my 7th term in this expansion. So there we go. That's just a couple of the things that we can do when it comes to looking at the general term of a binomial expansion, how we calculate it and how we write it in the simplest of forms. Something we have to be able to do in terms of manipulating algebra using the n's, the r's and our index operations. So if you can't quite remember that, go back and look at the Nat 5 stuff for your surds and indices. Just refresh your memory of what happens with each of the operations with the powers and with the same bases.